We studied Maxwell's equations in terms of potentials, namely scalar and vector potentials, and we derive a differential equations, a mixture of the coupled equations of the scalar and vector potentials. And under the Lorentz condition, we decoupled to the differential equations, and they show up as a non-homogeneous wave equations. One equation for the non-homogeneous wave equation for the scalar potential, the other is the for the vector potential. Lorentz condition del dot E plus 1 over C square del phi over del T. So you can look at your lecture notes. And the other case was the Coulomb. So that was the Coulomb gauge. And for the Coulomb gauge, the criteria is del dot A equal to 0, and this end up a Poisson equation, which already know the solution from the first part of the course. Scalar potential is 1 over 4 pi epsilon 0 charge density per x minus x prime magnitude integrated through the volume. And the other equation was coupled. So we decoupled that equation in terms of the potentials, scalar and vector potentials, and we put the equation in the following form. So for the vector potential, we deduce the equation del square A minus 1 over C square del square A del T square minus mu 0 transverse component of the current density. So if you look at your notes, you will see that the total current density could be written as transverse and longitudinal part, and by studying these coupled equations, we put in the form to this. And again, this is a non-homogeneous wave equations, but the source term in that case is the transverse currents. So basically, you can think about a solenoidal current. It's moving, circulating up and down. So Coulomb gauge is also called radiation gauge. So basically, in Lorentz condition and Coulomb condition, we have non-homogeneous wave equations. Then we said that let us solve this equation. Solution requires a calculation of the Green's function. So what we do, we write the scalar non-homogeneous wave equations. For the source, we put a delta function, delta x minus x prime, delta t minus delta prime. This is the unit source that is surviving under the integration of d cube x prime and dt prime. And on the left hand side, we have wave equation, and the solution is the Green's function, x prime t prime. So using the Fourier transform and inverse Fourier transform, we are able to get the solution. And what we do, we came up to following integral. We had a two solution, plus and minus, and physically one is the retarded Green's function, the other is the advanced Green's function. So basically that could be written as R tau. R is x minus x prime. X prime is the source location and x is the point of interest, and tau is t minus t prime. And if you look at your notes, that is 1 over 2 pi from minus infinity to plus infinity e to the plus minus I omega over c r over r and e to the I omega tau d omega. So this part I derived in the last time. So from now on, there is one correction in your notes. You have to handle that. That is very easy. So you can take the r outside the integral, 2 pi over r, and this is equal to I omega minus tau plus minus r over c d omega, and put the 2 pi here, 1 over r, and this is 1 over 2 pi, and this is a delta function of minus tau plus minus r over c. If you look at your notes, I put as a plus sign, so make a correction here. So that should be minus. Okay? And tau is t minus t prime, therefore minus tau is equal to t prime minus t, and altogether this turns to be delta function of t prime minus t. Take the minus parenthesis, and the rest will be plus minus turns to be minus plus. R is x minus x prime over c. So basically this all is the Green's function, 1 over r times that. If you think about an integral, this integral will be survive when this argument of the delta function is equal to 0, and that is when t prime is equal to t minus plus r over c. So what is the meaning of this? You have two options. T is equal to what? Minus plus x minus x prime over c. So what is the meaning of this? So if you pick up this, what is the meaning of this? T prime represents a source, something happened, radiation emitted, or okay, and the information in vacuum is propagated at what? Speed of light. Therefore, the time interval from x prime to x is delta x over c. So if you pick up this, what is the meaning of this? Minus sign. What is the meaning of the minus sign? T is equal to t prime plus delta x over c. That means that the event occur, then we see later. That is used for the retarded Green's function. The other sign will be, of course, the opposite. So in my notes from last time, I forget this minus sign, put the minus sign, now everything is okay. So why the people use the Green's function? Because using the Green's function, you can solve this for any source. So basically, take this equation, 1 over c square del square over del t square, and x, so let me write a little bit here, x prime t prime, and that is equal to minus 4 pi delta x prime delta t prime. Multiply the both sides with source. What is your source? Some source, f x prime t prime, and multiply this also f x prime t prime, and integrate through the x prime and t prime, volume and the time. So this should be integrated through the d cube x prime and dt prime. Okay, so d cube x prime integration makes the what? Fx prime is a fx, and integration of dt prime makes the what? T prime is t. So for the right hand side, you will obtain minus 4 pi fx xt. For the left hand side, you have what? This. Therefore, this whole bunch of integration, or the convolution of the Green's function with the source, is what? The solution. So that is the idea. This all stuff is the solution. And this is the solution of the non-homogeneous scalar wave function. So if you look at these conditions, this is already scalar. This is a vectorial equation. But if you look at the component-wise, x, y, z, they are component-wise are scalar. And for the radiation on Coulomb gauge, you have again non-homogeneous wave function, wave equation, sorry. So we know that the Green's function, then that means that we can solve every kind of non-homogeneous wave equation. So you can say that your general solution contains what? Wave equation with the homogeneous. That means that there is no source. You can say that where is this? You can equate the right hand side to 0. You can have some solution plus that. And that is, openly, that is nothing but delta t prime minus t minus plus x minus x prime over c d cube x prime dt prime. I forget one thing, but what I forget? 1 over r. 1 over r means 1 over x minus x prime. This term is 1 over r is x minus x prime magnitude. Now, so that's all for the Green's function. So we can solve the non-homogeneous wave equations. We can find the scalar potential and vector potential. That means that we can find the what? After finding the scalar and vector potential, we can calculate that the electric field and magnetic field. Now let us move on to conservation laws. So one is the Poynting vector. So Have you seen that the Poynting vector before? So some of the undergraduate in the first part of the course? Undergraduate, you saw, okay. So the idea was following. We have actually 3 conservation laws. One of them is the conservation of what? Charge density. Del rho over del T, del dot J is equal to 0. And the other will be the conservation of energy and the momentum. So basically, think about a charge. Think about a charge that is moving under the influence of some electric field and some magnetic field. You can write the Lorentz force. Lorentz force is F QE plus V cross B over C. That is the Lorentz force. Then you can calculate that the work done on the charge under these fields. That is very simple. The work is equal to what? F dot dx. Dx is a path element in 3 dimensions. So Lorentz force dot product dx is the work. You can automatically see that the dx and v parallel to each other, and that should be 0. The second one will be the 0. Or you can say that dx could be written as v times dt, and v cross b dot v will be 0. So the general rule, magnetic force does not do any work. Work is done only electric field. And if you write that the v times dt and you divide to the dt, you will get that the power is F dot what? Or you will find that the power is what? Q E dot V, because V cross B dot V will be the 0. So this is for single particle moving under the external electric and magnetic field. Now, instead of a single charge, if you have some charge density in the medium, then what you are going to do, you will replace the charge with the charge density. So we generally introduce that the charge is as prime. So okay, if you have some charge, your position vector is x prime, so you have some charge density. If you have some charge density, charge per volume, and if it is moving under the external field, the total power should be written in terms of integral representation. You have the charge per volume, therefore you need a volume element, and the rest will be the same. Then you should integrate this through the volume element. As a unit-wise, charge per volume times the volume element is the charge. Nothing is changed. Now, another thing, do you remember that what is the charge density times the velocity? Charge density times the velocity. Do you remember what is this? Charge per volume times velocity is what? Length per second. What will be cancelled? That will be charge per area per second. Charge per area per second. Charge per area per second is the current density. This is the current density. So this is the power. And actually at this point, what kind of power is this? Electric and magnetic field is applying a force on the charges in the medium, and we are measuring that the power on the what? Charges. So that is actually mechanical power. This term is mechanical. And if you have a wires on the system, that mechanical power should be converted into heat due to the Ohm's law. That you can relate this, because the current density could be written in terms of the conductivity times the electric field. That is the Ohm's law. Now, so the bottom line is the following: electric field that current density integrated through the volume. So these are depending on x prime in the medium. If you integrate this volume, some volume, and inside the volume there is the electric field and the magnetic field. There are wires here, charged particles, and so on. So that is the total power on those charges. Now, the E is the field, current density is the current density. And you can relate the current density to the fields using the one of the Maxwell's equations, and one of the Maxwell's equation is what? Modified Ampere's law. So instead of current density, you can write E dot curl of H minus del D over del T integrated through the volume. And now we will make a slightly modification. So some simple calculus we will use. You can write, we will need this term instead of divergence of E cross H, consider this. You can write this H dot product curl of E plus minus E dot curl of H. So you can derive this easily with the index notations, and that is correct at this point. So what term you have it? You have this term here, and instead of this you can write the two of them. So the equation above takes the following form: a volume integral. Instead of E dot curl of H, take this, put this other, you will get minus divergence of E cross H plus H dot curl of E, and the other last term is del D over del T dot E integrated through the volume. Okay? You have curl of E. Again, from the Faraday's law, instead of curl of E, you can write what? Del B over del T. So left hand side is a volume integral E dot J integrated d cube x prime. This is the power due to the mechanical power on the charge, on the wires and sources, let's say sources. And what you have here, you have here minus H dot del V over del T minus del D over del T E dot. this is minus, and everything is minus. I will take the everything to the minus parentheses. So I'll do this in a later. So let me write this as a divergence of E cross H, and everything is minus. This is plus, therefore in the minus parentheses, let's say. And what can I write in this term? What is this? You know that the answer. What is this? You know that the energy density. So what is the energy density? The energy density is E dot D plus B dot H of 1 over 2. Therefore, that term will be the partial time derivative of the energy density. So U is energy density, energy per volume, could be written as 1 over 2 E dot D plus B dot H. If you take the partial derivative, first you will take the derivative of this with respect to t, dot product this, then the partial derivative of d, dot product e, and you will have 4 terms, and if you combine those things, this is nothing but, that will be the following. So del u over del t will be h h dot del b over del t plus plus what? D del over del t dot e. You have 1 over 2 factor, you have 2 times derivatives, and other constraint d is equal to epsilon e, and similarly you have for the same thing for the magnetic field, B is equal to mu h. And so taking derivative, you can easily show that this is nothing but the partial derivative of the energy density with respect to the time. So take the parenthesis here, close here, and integrate through the volume. So we obtain this. So arranging the things in a single integral, this is volume integral, that is volume integral, you can write everything together. So in a single integral, you can write this a volume integral of what? Take the others, so that will be divergence of E cross H plus del U over del T plus J dot E integrated through the volume have to be the 0. So that tells you that divergence of E cross H plus del U over del T is equal to J dot E. So at this point, as a unit wise, what kind of units we have? This is the power, this should be a power, and E cross H is the Poynting vector S, is the Poynting vector, And the unit of this is a vectorial quantity, but what is the unit of the Poynting vector? Energy per second per area, energy flux. Energy per second per area. That is the unit. And so basically we have one equation which is called del U over del T plus divergence of S is equal to minus J dot E. So if you make a comparison this equation with the continuity of the charge density, what is the difference? What is this? Charge density per time plus divergence of J is equal to 0, but in that case you have a sink term with the minus. So if there is no any source in the volume, this will be 0, that is a continuity equation, but here you have a continuity equation with the sink term. So what does it mean? What can you say for this equation? For the right hand side you have some power loss due to the what? The motion of the charged particles. Why the charged particles are moving? Because of the electric and magnetic fields. There is some power, dissipation, thermal energy. But on the left hand side, that should be equal to change of the total energy density. What kind of energy density? Energy density of the electric and magnetic fields plus delta S. What is the meaning of the delta S? That is the energy escaped from the closed boundary. So we can represent this equation in the integral form, and we can understand that what the divergence of S doing more clearly. So let us write this equation in the integral form. So in the integral form, that equation is equal to following. So let me take the delta S in the one side, the rest of the other side, and so let me write in that form. And integrate this through the volume. And you have J dot E integrated through the volume, and del U over del T integrated through the volume. They are all integrated through the same volume, and from the divergence theorem this turns to be a surface integral. What kind of surface? The surface of the closed volume. We choose S dot and dE. And go to the right hand side. What was the definition of the J dot E integrated through the volume? Remember, that was power. Power means that d work done by dt, or power is the same, but energy per time, rate of the energy. What kind of energy is important here? Mechanical, because this is due to the currents in the system, sources. So basically that term O is d over dt of mechanical energy. So do you have a question here? So this is the sources. There are sources, and the fields is what? Doing some work on these sources. Therefore, there's some power generation, but they are all mechanics. Okay, motional. And if you look at this term, you can take this to the outside, del over del t, u d cube x. What is the integral of the energy density through the volume? It's automatically, you know, that is the total energy. But total energy of what? Total energy of fields, E and B fields. So basically you have total energy of the fields. Then, so there's one trick here. You see maybe in other courses like relativistic quantum mechanics. So if you take this partial derivative outside, generally we can write as a d over dt. Do you know why we do this? So do you remember this? This is the reason. So this is the partial derivative because this u is depending on t and the position. But if you take the integral, only dependence is the time. Therefore, you can write as an exact derivative, not a partial. So what does it tell us now? That tell us the following, this equation. Integral presentation. This is the differential presentation. Integral presentation tells us that the following. Suppose that we have a closed volume. You have some electric fields and some B fields, some wires. On the wires there are some currents. So at the surface of the volume, some energy is escaping, S. And you have the surface unit vector N, this one. Okay, at the surface some energy escaping at the surface, but inside the amount of the escaping intensity through the surface is equal to what? Sum of the change of the mechanical energy in the wires on the sources plus the change of the total energy due to the fields. Okay, so that is another meaning, so they are the same. So bottom line, it is called as a conservation of energy because nothing lost. So the escaping intensity through the surface is equal to the rate of change of the mechanical energy plus rate of change of the field energy. So this is called a conservation of energy. And other equation, continuity of the charge density. Next thing, we are going to show you that the conservation of linear momentum. So let us try to study the conservation of linear momentum. So start again a Lorentz force. And that is equal to momentum rate of mechanical rate of the mechanical momentum. And instead of single charge, if we have some charge density in the medium, you can write this as a charge density. Therefore, you should write the volume element here, and E plus V cross B. And if you distribute the charge density, you will get rho E, rho V cross B, d cube x prime, and this is equal to current density. So once we saw that the current density, so as you see that the left hand side is the mechanical force or the rate of the change of the mechanical momentum, right hand side contains the current density, but current density could be expressed in terms of the fields using the Ampere's law. Charge density could be represented in terms of the fields using the first Maxwell's equations. So basically what I am going to do is the following. We have something here. For that term, we have what? Rho is the divergence of what? Electric field. Okay, rho is the divergence of electric field from the first Maxwell's equations. Source of the field is the charge density. For current density, we should look at the following. So what we have for the current density, 1 over mu 0 curl of B and minus epsilon 0 del E over del T, cross product B integrated through the volume. This is equal to what? Curl of H is equal to what? Curl of H is equal to current density plus del displacement current over T. So I'm trying to write this in vacuum. So mu 0 epsilon 0 will be 1 over c square. So if I take the everything in the epsilon 0 parentheses, what I am going to obtain? Epsilon 0 so rho was equal to, remember the del dot E is equal to charge density, so that is equal to epsilon 0 E. If the medium is the uniform, that is equal to that. Therefore, I forget to write the epsilon 0 here, and I have a E here. So if you take the epsilon 0 parentheses, you will obtain E, divergence of E, so change the order of cross product, write B cross del E over del T. So you change the order of the cross product. If you take the epsilon 0 parenthesis, this will be 1 over epsilon 0 mu 0, that is c square. So you will have c square. If you change the order of the cross product, B cross curl of B, we will obtain integrated through the volume. So this is the rate of change of the mechanical linear momentum in time. So we will play this equation. So let me play a little bit. So we will put this in the nice form. One of the things we can do is the following: B cross del E over del T. What is this? That is equal to, so B cross del E over del T is equal to minus del over del T E cross B plus E cross del B over del T. Take this to the here, and this is simply derivative. So del E over del T cross B, the order is changed, that becomes B cross del E over del T, and this is equal to minus del over del T E cross B minus del E over del T E cross B, E cross plus E cross del B over del T. What is the del B over del T? From the Faraday's law, that is equal to minus curl E. Okay, from the Faraday's law. So basically that is equal to minus E cross curl of E for the middle term. So let me go one line and then we can give a break. Lorentz force on the left is equal to epsilon 0 E times divergence of E. At this point I will introduce a term that is effectively 0, but it will create a very nice symmetry. That is what actually, if you look at here, what Maxwell's equations we use so far. We use that the first Maxwell's equations, we use that the modified Ampere's law, we use that the Faraday's law somewhere here. So we use the three of them. What we didn't use, we didn't use yet magnetic, there is no magnetic monopoles, del dot B. Del dot B is equal to 0, but for the symmetry points of what we are going to obtain, I would add up a 0 here. C square B del dot B. You will see that the effect is nice. So that is 0, but you will get a very nice tensor at the end. I add that term, so basically I use this term. I add at the del dot B there, so let me use this term, and that is equal to minus E cross curl of E, and I use this term. Then let me use this term, minus C square B cross curl of B, close the parenthesis. So I use this term also. What is left over? This whole term is left over. So then go one more step, and the leftover term is equal to leftover term is equal to del over del t E cross B, and everything have to be integrated through the volume. So one thing here before I'm going to stop, you have epsilon 0 times this term. What is the E cross B? Poynting vector. So related with the Poynting vector. Actually, E cross H is the Poynting vector. So let me take this to the left hand side. So left hand side will be the what? dp mechanical over dt, and that goes to the left hand side as what? A volume integral del over del t E cross B d cube x prime. I forget one thing. What is this? Epsilon 0. Epsilon 0 here. And the other terms will be written again there. So all I do, I take this to the left. So what could be? So I can switch the integral and the partial derivative. As I said before, that becomes d over dt, because we take the volume integral, then del over del t is replaced by d over dt, and we get epsilon 0 multiply mu 0 divide by mu 0, and that will be E cross H d cube x prime. Still I am on the left hand side, and this is the dp mechanical over dt, and E cross H is the Poynting vector. And what is the unit wise? What is the unit force? Since this is a momentum, this whole stuff should be momentum. Therefore, that should be equal to what? Mu 0 epsilon 0 is 1 over c square. E cross H is what? S. And this is the integral of this through the volume. So all stuff have to be momentum, because this is the derivative of the momentum. Therefore, integrand should be what? Integrand should be 1 over c square E cross H should be what? E cross H over c square, or S over c square should be what? Since the integral is momentum, so volume integral is momentum, therefore they should be what? Density of the momentum. Momentum per volume. So this is called as a G, and that is called as a electromagnetic momentum density. Why? Because if you take the volume integral, you are obtaining the momentum. So basically you need a E and H field in order to obtain a density of the momentum or momentum. So in next hour I will study the rest of the terms. Okay, let us stop there and we can continue 10 minutes later.